we know that there are three of Newton's laws of motion. We've met the first and the second, so obviously there's one more to go. That would be Newton's third law of motion. Um, Probably have heard it described as for every action, there's an equal and opposite reaction. That's not exactly the most useful way to phrase the idea of Newton's third law of motion, because it implies perhaps that there is some difference between the thing that you call the action and the thing that you call the reaction. Also, action means something different in physics, um, not really captured by that statement of Newton's third law. So when we're thinking about physics carefully, we try to move beyond that colloquial phrase. We're actually going to express Newton's third law of motion as a vector statement, but I try to motivate that vector statement a little bit first. Whenever I have two objects interacting with each other, they do so by exerting forces on one another. Those forces have to come in pairs. And that pair of forces, an interaction pair of forces, has a special property. So when two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. So if I were to lean up against a wall, in my interaction with the wall, no matter how hard I pushed on the wall, I know the following is true: the force that I exert on the wall is equal and opposite to the force the wall exerts on me. And that's what I'm trying to capture here with this notation. So the wall comma me means the force that I exert on the wall, the me comma wall meaning the force the wall exerts on me. So those two are equally strong, but they point in opposite directions. So that's how we get this equal and opposite phrasing that pops up in physics and not so much in other fields. The interaction pairs from Newton's third law are always going to be of this form. I have a force uh, B on C is equal and opposite to C on B. So there are always two objects interacting. And then the concise statement for Newton's third law of motion is as follows, just this vector statement. For any B and C, which are two objects or two bodies interacting with each other by exerting forces, those forces are related as being equal and opposite. A little bit of an aside to set context for things here. Newton's first law of motion uh, is not the final form as we have learned it. Um, Newton's first law of motion can be extended, and that's the role of the general theory of relativity. And that extends Newton's first law of motion to also include um, situations where the only force acting on the body is gravity. So it doesn't have to be no force, it could be uh, either no force or only a force of gravity. And instead of moving with a constant velocity, we generalize that to the trajectory the object follows, a geodesic. So that what is general theory of relativity generalizing Newton's first law of motion to also incorporate gravity. Newton's second law of motion, as we have learned it so far, that add up all the forces, that equals mass times acceleration. That's actually only the case if the mass is constant. If the mass is changing, then we actually have the more fundamental statement that we'll get to later in the class about the sum of the forces causes a time rate of change in momentum. With that form of Newton's second law of motion, that gets modified in the special theory of relativity because momentum gets modified in the special theory of relativity. So that's not a complete and done thing. We'll come back and tinker with and change the second law of motion. And then also, the second law of motion is very important for the sorts of physics that we're doing in this class. But when you get to the quantum scale of physics, or what's referred to as classical mechanics, you don't use forces so much. Instead, things are phrased in terms of an energy formalism. So while Newton's second law of motion, sum of forces is equal to ma, or the sum of the forces causes the momentum to change at a certain rate, that's sort of fundamental for us now. Those are sort of supplanted and don't even really make sense in a quantum system until you have enough objects interacting together on the quantum scale to get something that behaves like a classical particle. So that's all just to say there's a lot more to physics. Those other things in physics are changing the first and second of Newton's laws of motion, but there are no changes whatsoever to Newton's third law of motion. So Newton's third law of motion, as far as we know, is really, really true. And even working on physics for 4 centuries, there are no changes, no modifications, no exceptions, no anything for Newton's third law of motion. It is the one that is still in its original form, all up to the present day. So really, 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 really true. So even when you forget it on a problem, it still is really true. All right, so let's practice with this idea of Newton's third law of motion with some questions. All right, a person pulls a box across the floor. Which is the correct analysis of the situation? Read through all 5 possibilities. Only one of them is correct. So read through all 5 possibilities. Keep in mind Newton's third law of motion is really always true, and try to discern which is correct in terms of physics. Talk it over with your neighbor, your physics friend, and then when you're ready, unpause the video and we'll go over the answer together. All right, so a person pulls a box across the floor. So certainly an everyday sort of thing. Which is the correct analysis of the situation? So let's go through and talk about all of them. The box moves forward because a person pulls forward slightly harder on the box than the box pulls backward on the person. That cannot be the case. That violates Newton's third law of motion. The person can't pull forward on the box harder than the box pulls backward on the person, even just a little bit. Because action always equals reaction, the person cannot pull the box. The box pulls backward just as hard as the person pulls forward. So there is no motion. Well, you got to school somehow today. Motion is possible. So it's not 2. 3, the person gets the box to move by giving it a tug, during which the force in the box is momentarily greater than the force exerted by the box and the person. We cannot violate Newton's third law of motion, not even for just a little smidgen of time. At every instant of time, Newton's third law is true. The person's force on the box is as strong as the force of the box and the person. Check. So far, so good. But the frictional force on the person is forward and large, while the backward frictional force on the box is small. That's how you're able to get the box moving. You are going to exert a force backwards on the ground through static friction of your feet on the ground, and as the interaction partner to that is going to be the static force of friction before forward on you. If that forward force on you is greater than the backwards pull from the box, then you can accelerate the box forward. And so that is possible if I have a net force pointing forward. Okay. All right. The person can pull the box forward only if he or she weighs more than the box. This is it's a really popular answer. It's a surprisingly popular answer. It might have been your answer. But weight is the force of gravity which acts straight down. That has nothing to do with the forces in this question, which are in the horizontal direction. So it is 4. Let's try another one. Consider a horse pulling a buggy. Is the following statement true? And this winds up sounding a little bit like a Dr. Seuss thing. But forgive me. The weight of the horse and the normal force exerted by the ground on the horse constitute an interaction pair that are always equal and opposite according to Newton's third law. Is that answer to that true? That the statement is true? Yes. Or is the statement false? No. So read it through carefully, check in, see if you have consensus with your physics friends, and then unpause the video and we'll talk about the answer. All right, the answer is no. And I'm going to be very clear about the reasoning why. The weight of the horse is the force of Earth's gravity pulling on the horse. So it's a force on the horse. The normal force exerted by the ground on the horse is, again, a force on the horse. Okay. So I have two forces on the same object. This cannot be cast in the form of F of C on B is equal to minus F of B on C. Okay, they cannot be equal and opposite because I have, in fact, three different objects interacting. I have the Earth as a total exerting a force of gravity on the horse. So it's two objects, horse, Earth, and then I have the ground and the horse. So that's the horse again, and then the ground. Okay. I'm not going to have an interaction pair of forces that are always equal and opposite out of these three interacting objects. Okay. They happen to be equal and opposite because of Newton's first law. The horse and the buggy is not accelerating up into the air or falling through the ground. I have equilibrium. So they're equal and opposite because of Newton's first law. They are not compelled to be equal and opposite in all situations by Newton's third law. If you think about this, if your answer to this is yes, you are saying that no one can jump up in the air. Okay. How do you jump up in the air? You push down on the ground with a force greater than your weight. Therefore, the ground, through Newton's third law, pushes up on you with a force greater than your weight, and you're able to accelerate up into the air. Okay. The forces that are compelled to be equal and opposite are, we'll start off with the most straightforward one because it's contact force, right? The horse pushes down on the ground just as hard as the ground pushes up on the horse. Those are always going to be equal and opposite. The other pair that's always equal and opposite is the force of Earth's gravity pulling down on the horse is equal and opposite to the force of the horse's gravity pulling up on the entire Earth. Okay. It's always that form C on B and B on C. All right, let's try another one. Water skier is being pulled by a rope attached to a speedboat moving at constant velocity. Consider the following four forces. 1, the force of the boat pulling the rope. 2, the force of the skier pulling on the rope. 3, the force of the boat pushing the water. 4, the force of the water pushing on the boat. Which two forces are an action-reaction pair that is consistent with Newton's third law of motion? There's only one correct answer. So go through and try to figure out which of those of the four forces, which two are related together as being an action, reaction, or interaction pair consistent with Newton's third law of motion. Once you think you have the answer, consult with your physics friends and see if you have consensus, and then you can unpause the video and we'll talk about the answer. So the answer is forces 3 and 4. And you look at the wording of them, they're just those two objects, the boat, water. The force of the boat pushing the water is always equal and opposite to the force of the water pushing on the boat. Okay. You might have wanted to say that the force of the boat pulling the rope is equal and opposite to the force of the skier pulling on the boat. That need not be the case. Okay. Force 1, the interaction partner would be the force of the rope pulling on the boat. For 2, its interaction partner is the force of the skier, or the force of the rope pulling on the skier. Those are always equal and opposite. Okay. Not necessarily the case that the force of the skier on the rope is equal and opposite to the force of the boat on the rope. Okay. Those are, again, 3 different objects. Newton's third law guarantees that interaction pairs are equal and opposite, but that's going to be 2 objects interacting with one another. So the force of the boat pulling the rope would be always equal and opposite to the force of the rope pulling on the boat. And the one that is actually interaction pair out of these 4 forces, force of the boat pushing the water and the force of the water pushing on the boat. Those 2 are always equal and opposite. Okay. Astronaut is on a spacewalk outside her ship in gravity-free space, which we know is not actually gravity-free. There's plenty of gravity there. It's just everything is falling the same way in free fall. Initially, the spacecraft and astronaut are at rest with respect to one another. Then the astronaut pushes to the left on the spacecraft, and the astronaut accelerates to the right. So it'd be like, which of the following statements concerning this situation is true? So there are 5 statements of physics there. Which one of those is true? All right. So this is a sort of a summary question for all of Newton's laws of motion together there. It is not, A is not true. The astronaut stops moving after she stops pushing on the spacecraft. No, Newton's first law of motion, after she stops pushing on the spacecraft, then she's going to keep moving. It would take a force to stop her. The velocity of the astronaut increases while she is pushing on the spacecraft. That is true. That is consistent with Newton's second law of motion. While there is a net force acting on the astronaut, because the astronaut is pushing on the spacecraft is pushing on the astronaut, the velocity of the astronaut will change. Okay. The force exerted on the astronaut is larger than the force exerted on the spacecraft. That's impossible. The astronaut can push no harder on the spacecraft than the spacecraft pushes back on the astronaut. That would violate Newton's third law. The spacecraft does not move, but the astronaut moves to the right with a constant speed. So it might sound reasonable, but okay, it can't be true that the spacecraft does not move. That would only be the case if the spacecraft had truly an infinite inertia. Okay. So we know that the forces are equal and opposite the force of the astronaut pushing on the spacecraft, the force of the spacecraft pushing back on the astronaut. Then you go to Newton's second law of motion. The forces are equal and opposite. The object with the large inertia has a small acceleration. The astronaut with a smaller inertia has a larger acceleration. These are why in our interactions with Earth itself, I can bounce a ball off the Earth, I can jump off the Earth, I see that body object moving, I don't see the Earth move. Okay. That's because Earth has vastly more inertia than I do or a ball does. It doesn't mean Earth did not move, just moved imperceptibly small amount. Right. Then the last one, the force exerted on the spacecraft is larger than the force exerted on the astronaut. So the same problems we had with C. That violates Newton's third law of motion. Cannot happen. Newton's third law of motion is really, really, really true.